Okay, so we're up to step 3 now for solving the electric field for the uniformly charged long thin rod. And we've gotten to the point where we have an expression for the electric field, which is only along the x-axis. And our expression is for the small contributions that are going to be added up for each small segment delta y along the rod. And so that looks like 1 over 4 pi epsilon naught q over L x over x squared plus y squared to the 3 halves times delta y. And we could take this rod and break it up into as many segments delta y as we're willing to do this calculation for. Turns out that that's a really tedious thing, because if we want an accurate result, we want the delta y to be as small as possible. And so if this rod is really long and we break this rod into 1,000 pieces in order to get an accurate result, then that's 1,000 calculations that we have to do. And you can look in the book in figure 15.7, they show you how to break this into pieces. And then based on the number of pieces that you break it into, the number of slices, you can see how the electric field is changing when you add all of those up. And somewhere around 50 or 100 pieces, you start to see the total electric field, the net electric field, to converge towards a single value. But who wants to add up 50 or 100 slices of this rod? So what we do instead is we use calculus. And in calculus 2, you'll learn about the integral. The integral is simply summing an equation. You're just breaking the equation into tiny pieces and then adding each of the tiny pieces up until you get the sum of that equation over some range that you're interested in. So all that means is that when we let these deltas become very, very small, in calculus we tend to convert those into d's to indicate that they've become infinitesimally small. And we would just rewrite this equation as 1 over 4 pi epsilon naught q over L x over x squared plus y squared to the 3 halves times dy. And if we want to then sum up all of the contributions from these small intervals, we have to write this as an integral, which is just sort of a skinny s, you might think of it as. And so in calculus, really the integral is just the antiderivative. And so you can kind of think about it as, when you look at this formula here, you would ask yourself, what formula would give me this formula as its derivative? That's what doing the integral is. And this one is fairly complicated. But one nice thing that we can do is we can take anything that doesn't, since we're calculating an integral here that has to do with y, we can take anything that doesn't have y, we can take it outside of the integral because it's not going to have an effect. It's just treated as a constant. It doesn't matter which y value we choose, where we are along the rod, all the x's and the l's and the q's are going to be the same. So we could write this as the integral of dE x is equal to 1 over 4 pi epsilon naught q over L, and then we can take that x out. And so we just had the integral of 1 over x squared plus y squared to the 3 halves dy. And we can't separate that anymore because that x squared plus y squared raised to the 3 halves is all one term that's in the denominator, and there's no further simplification we can do. But this is the kind of formula that you can simply look up in a book, or you can go to Wolfram Alpha, or you can use all sorts of computational techniques to tell you what that integral is. We won't worry about what the solution is just yet. Before we do this, we need to decide just what length of rod we want to do this summation over. So we're trying to sum up all of these small intervals dy over the entire rod. So we need to define the length of the rod relative to the origin. So we know the origin has been described as being right in the middle of the rod. We do that for convenience so that these y components cancel one another. So we really want an equal amount of rod above the origin and below the origin so that when we look at the axis along the origin that cuts through the origin here, we get that cancellation. And so we're just going to define this rod to have a total length of L, because that's what's in our formula here. Is the length of the rod L contains a total amount of charge Q. And so we want half of that rod to be below the origin. So there's a length here, but it's in the negative direction. And we want half of the rod to be above the origin. And so we might say that this position along the y-axis is L over 2 at the very top, and this position on the y-axis down at the bottom is minus L over 2. That means that we want to sum up all of the dy's along that rod from minus L over 2 to L over 2. And when we do that, we've summed up over the entire length of the rod, and so we expect this part to give us the total electric field along the x-axis, because that's the only direction the electric field will point. So this integral on the left-hand side of the equation is just Ex. We're going to, anytime you integrate just d something, you're going to get whatever the something is. So now when we do the integral, this previous step here, we call the indefinite integral because we haven't defined any sort of limits that we want to integrate over. And then this we call the definite integral because we've defined the limits over which we're going to do the summation. And once we get an answer to this, that gives us the electric field. We're done. So that's the subject of the next video.